Hey, Algebra 2 honor students, this is Unit 2, Day 3. We're going to be looking at two pretty big ideas today. We're going to talk about compositions of functions and the concept of what it means to be one-to-one. Maybe that's something you learned in Algebra 1, but if not, we're going to recap that concept today. So let's start right away with a definition for what a composition of functions is. A composition of functions is when the output of operating on one function is used as an input to operate in another. So what we're going to see is in this first example, we're given two different functions that are defined, and we need to talk about some of those notations down there. So first of all, one of the notations we might see is f of g of x, and that's how both of these would be read. So I would read this mathematical statement as f of g of x. So we're going to operate on that g function first that's on the inside, and whatever that result is, that gets plugged into the f function that's on the outside. This notation means the same thing as this one. This is read as f of g of x. So you would do g of this input first, and whatever that result is, whatever the output is, we plug it into the f function. So once we get used to the process, these go pretty quickly. If I look at the first example, f of g of 1, we have to start on that inside piece first and do g of 1. So to compute g of 1, we know that we just input 1 for x in the function defined by g of x. So 2 times 1 plus 3, well, hey, 2 plus 3 is 5. And then from there, whatever that result is gets plugged into the outer function, which is the function f of x. So f of 5, if I come to the function f of x, 5 squared is 25. Minus 5 from that is 20. So the total value for f of g of 1 would be 20. That would be the final answer there. Okay, so you don't have to box in that midway answer that we got for g of 1. Make sure that you plug that into the outside function and get your final answer. You can see I've circled some questions that we're going to work on here, so maybe we'll use some of the others for practice in class, but let's go on to number 3. This one says g of 0. It's a little bit odd to have the same function twice here, but that's okay. We just want to make sure we use this g of x function in each case. First thing I'm going to do is compute g of 0. And to do g of 0, we would plug in 0 for x there. 2 times 0 plus 3 would be 3. And then whatever that result is, that output, input it to the g function again, whatever that function on the outside is. So then to do g of 3, it would be 2 times 3, which is 6, plus 3, which is a final answer of 9. So evaluating within compositions, as long as we're familiar with the notation, really not that challenging. I do want to make sure we take a look at this different notation. That open circle implies a composition of functions. Students will sometimes confuse this for multiplication. I'll tell you, we know we should be multiplying if that's a closed filled in circle. But with the open circle that's listed here, this is the same thing as writing g of f of -3 with the notation that you see up here. These two things mean the same thing. So what that implies is that you do have to do f of -3 first. So f of -3 would be -3 squared minus 5. When you plug in -3 to that squared piece, make sure you put -3 all in parentheses. So when I square that, that becomes positive 9 minus 5, which is 4. And then g of 4, that last piece would be go to the g function. 2 times 4 is 8, plus 3 is 11. Okay, so just be a little bit careful about some negative inputs at times, but other than that, I think we'll be good to go when evaluating some compositions. So to get a little bit more practice with this concept, you can see down below we have two graphs that are given, one for f of x and one for g of x. And evaluating based on a graph can be accomplished just as easily. You can see I have some examples circled down here as well. We'll start right away with number 2, which says to compute f of g of -1. So the first thing I have to do is figure out, well, what's g of -1? Do that inside part first. Make sure you're looking at the graph for g of x when we answer this. We want to figure out if the input for x is -1, what's the output? So the output there is 1, 2, 3, 4. It looks like -5. It's a little tricky towards the end here when it gets a little steep in this parabola here, but I'm going to say that g of 1 or -1 is -5. Well, I take that result and then I plug it into the f function. So what's f of -5? 1, 2, 3, 4, 5. When the input for the f function is -5, the output there looks like it's going to be, let's say, -1/2. Okay, so the final answer here would be -1/2. If at any point you want to pause and try these and see how they go for it. Okay, different notation again, g of f of negative 2. The first thing you would do here is f of negative 2. This is the same thing as writing this statement, g of f of negative 2. So let's make sure we use the f function first. F of negative 2, when the input's negative 2, the output is 1. Go ahead and use that in the g function. G of 1 is 1, 2, 3. Final answer. Okay. One more to go. And again, if you use the same function twice, that's okay. This is the same thing as f of 0. So we can ignore the g graph for this last example in number 6. If I do f of 0 first, f of 0 is an output of 2. And then finally, f of 2 would be if I go over 2, 1, 2, 3. So the final answer for f of 0 is 3. So if you have any questions about this, certainly we can do some other examples in class that I'm saving here. But what that leads us to is, what if I don't give you a specific input value for x? So the next page has compositions of functions in terms of x. So given f of x and given g of x here, we want to evaluate these two compositions. So the first one says to compute f of g of x. So again, there's no specific value here. It's not f of g of 2 or f of g of negative 3. It's just f of g of x. So what we'll see in both of these examples is that your final answer will have x's in it. It will be in terms of x. And in order to accomplish this, what I like to do is I replace the inside function g of x with what it equals, 5x plus 4. So what I'm asking you to do is go to the f function, and wherever you see that input of x, which is right here, we're going to replace that x with the entire quantity 5x plus 4. So that would be 3 times the quantity 5x plus 4 minus 2. That can take a little while to get used to when you're inputting a whole function for x or a whole expression here. But then to simplify this, you would distribute the 3. So 15x plus 12 minus 2. And then finally, the last thing you could do in this case is just combine the like terms with the 12 minus 2 at the end to get 15x plus 10. And that would be your final answer, 15x plus 10. It seems like there should be more to do with that, but that is where we stop. Nothing else to do there. Okay, g of f of x. So this will be the same thing if I just reverse it. That would be kind of nice, then I don't have to think too much about it, but let's see. So f of x, that function is 3x minus 2. So what we're going to now do is take this function, 3x minus 2, and we're going to plug it in for x in the f function. Okay, do the reverse here. So when I input f of x to the g function right there, it would be 5 times 3x minus 2 plus 4. Okay, clean it up just like I did over here. Distribute the 5 to get 15x minus 10 plus 4. And after combining like terms, last step, you get 15x and then minus 6 at the end. So they're pretty close to one another. But in the end, they are very clearly different expressions, f of g of x versus g of f of x. So if there's anything to take away from these two examples, it's that the order is important. The order in which you plug into a composition matters. We didn't really discover that too much on the front page because we never did like f of g of 2 and then g of f of 2 to see if they were the same. But this is a clear indication that they're not going to be the same. Maybe under special circumstances, but most of the time, and especially in this first case here, the compositions in both directions result in different expressions, okay? As you can see, this example right here, let's save that one for class. We'll do that one together next time we're all together here. But let's do this application. I like this question. It says water dripping from a faucet creates a circle in the basin of a sink. So maybe you can picture that, right? Water's dripping down. And then as that puddle in the sink gets bigger and bigger, it's a circle that as it drips, maybe the circle's expanding. If the radius of the circle is expanding at a rate of 2 centimeters per second, determine a function that models the area of the circle as a function of time. So what I like about this question is typically area of a circle is not a function of time. Area of a circle is usually a function of its radius. And maybe we wouldn't have used this notation typically, but area of a circle is in terms of whatever the radius of the circle is. And I'm hoping that if I asked you in class, you would all say area of a circle is pi r squared, right? You probably just would have written a equals, but I like the function notation piece here, and you'll see why in a minute. Okay. Now, what we're saying is that that radius is changing as time goes on. It's expanding at a rate of 2 centimeters per second. So we can define a function called r of t. This is the radius as a function of time. And I know that that's 2t. So as time goes on, if this is in units of centimeters here, this would represent the radius of the circle as time goes on. Well, in the end, it says find the area of the circle as a function of time. So to get the area in terms of the time, what are we asking to compute here? It's the composition A of r of t. If I take this function right here, r of t, and I sub it in for r above it, that's going to give me an area model that I can figure out what the area is as time goes on. Not dependent on the radius anymore, but dependent on how much time has elapsed. So what would that look like? It would take the function r of t, which is just 2t, and we're going to plug that in for the radius right here. So that would be pi times 2t quantity squared when I plug that in here. And 2t squared is going to be 4t squared, so make sure you square that 2 as well. I'm just going to take that 4 and pull it to the front. That's typically how you would see it listed in a coefficient form. Okay, that 2 squared of 4 got pulled to the front. This expression right here is the area of the circle as a function of time. If I said how big is the circle area-wise after 10 seconds, we would just plug in 10 for t, and we can determine that area fairly quickly without even thinking about what the radius is anymore. Okay. So I like this question just in terms of like, well, why do we need function composition? Here's an example of where it might be pretty useful. Okay. The last main thing we're going to talk about for today is examining what makes something one-to-one. So it says to determine that what makes something a function one-to-one, let's consider the following examples. We have function f of x, which is 2x. We have the function g of x, which equals x squared. Map the domain -2, 0, and 2 using each function in the space below. So we have a domain of values. I want to see what the range is for these two different functions. Let's start with f of x. F of x equals 2x. So 2 times -2 is -4. 2 times 0 would map onto 0. And then 2 times 2 would be 4. Okay, so there would be the mapping that you would draw for the function, the elements of this domain to the elements of the range. Now on the other side where we have the function g, if g of x is defined as the function x squared, -2 squared is 4, right? Make sure you put parentheses around your -2 before we square it. 0 squared is 0. And finally, the last input for the domain of g, 2 squared. It's not a new range value. It's not a new output. 2 squared is 4 again. So that's the connection. That's the mapping I would draw for that last case. So what is the difference? I'm hoping it's pretty obvious now that we've drawn these mappings. Right here, we have an output that belongs to 2 different inputs. Whereas here, every single input had a unique output, and every single output has a unique input. So what I would say is that in the first case, for function f, there is what we call a one-to-one correspondence. Right? Every domain has a unique range, and vice versa. Every range has a unique domain that it corresponds with. But in the second case, for function g, and it is still a function, right? Every input does have a unique output, but the output of 4 corresponds with multiple inputs. And therefore, we would consider that g is not that one-to-one correspondence. Okay. And that's what our definition of one-to-one will be. You'll see if you turn to the next page. So on page 24, we have a definition that we're going to write for what it means to be one-to-one. So let's go ahead and do that right now and fill in the definition here. The definition states a one-to-one function is when each input has a unique output and each output has a unique input. And that kind of makes sense, right? So we have this one-to-one relationship. that every domain value pairs with a unique range value, and then vice versa there. Okay. So what I want to do is, in a few different instances, analyzing some information about a function, or maybe it's not even a function at all. But we want to look at some information to determine, is it a function, like in these tables here? And then is it in fact a one-to-one function? Does every domain value have one range? And does every range have one domain that it corresponds with? Okay. So if you have that definition down, let's take a look at the tables here. In the first example, is it a function? Well, if you have an x value that corresponds with two different y values, that's what we're looking at to fail the function test. Okay, each input doesn't have a unique output, so that's a problem, which means that one-to-one is not even assessed. You can't be one-to-one if it's not a function, so that's kind of nice in the fact that one-to-one can only apply if it's a function to start. Are there any repeating x values in the next case? I'm not seeing any in that table, so I would say yes to function here. But does every output have a unique input? And what we'll find really quickly if we analyze the y column is not quite. The output of one has two different inputs that it pairs up with. If it was a mapping example, there'd be two arrows drawn to the output of one. So I would say no, this is not one-to-one. If we analyze this case, 1, 2, 3, 4, all different inputs, so we're good for function. Do we also have all different outputs? 2, 4, 8, 16? Sure do. Okay, so that's the best case to determine a one-to-one function. And finally, the last example, -3, -2, -1, oops, back to -2. Because these inputs go to two different outputs, that breaks our rule to make it a function, and therefore one-to-one is not even applicable there. So this is kind of the best case scenario for us here in terms of looking at a table of values that would be one-to-one. That meets both criteria. It's definitely a function, and then every output is unique to correspond with those inputs. So that's what we're looking for to make it one-to-one. Last thing we'll do in this lesson is looking at a graphical test for determining one-to-one. So in each step below, determine which graph represents a one-to-one function. Well, first of all, to be a function, it has to pass the vertical line test. So this is definitely a function. Is 2 a function? Vertical line test? No, it hits multiple outputs there, so that's no good. Same thing for the circle in number 3. This would fail the VLT. So these two graphs are not functions because they fail the vertical line test. So we're kind of narrowing it down to 1 and 4, and which one of those is one-to-one? Well, now that I know that these pass the vertical line test, does every output, does every y value have just one input that it goes with? And if we look at the first multiple choice, this parabola here, we're going to find an issue here, right? So the output of, let's say, 2 on the y-axis would have two different inputs. So there's no one-to-one correspondence there. So it's not choice 1 either. The best case scenario is choice 4 here, because every output has one input and every input has one output. So we're going to generalize this to a specific test in a moment here, but see if you can pick out the correct answer for the other set of multiple choice. Which one of these would be a one-to-one function? Maybe it's pretty obvious right from the start. I'll go through the answer now. 1 is definitely not even a function, fails the vertical line test. Okay. All the others pass the vertical line test, but the only one that happens to be one-to-one is choice 3. Because what we're looking at is, hey, check out that output right here. It has 1, 2, 3, 4 different inputs. Definitely not a one-to-one correspondence there. And same thing for the parabola. It's just like the parabola that was graphed up here. So this is the only one with a one-to-one correspondence. In order for the graph to be one-to-one, it must pass the, well, first of all, vertical line test would be pretty important. And how about the horizontal line test? That's what I was drawing in each of these cases. Okay, so it also has to pass the horizontal line test in order to be considered a one-to-one function. So we'll stop there for today. We do have one more page left in the notes. It's page 25, and we're going to work on this next time we're together. So save that page for class. We have one more definition to talk to and a little bit more practice at the top. But that is it for Unit 2, Day 3. Have a great rest of your day.